In electrical circuits, the sine wave can be represented as A sine omega times time plus or minus phi, where A is the amplitude of the wave and omega is the angular speed and phi is the phase shift. The rectangular representation of a sine wave can be described by the sum of its imaginary and real parts. The x-axis describes the real part, while the y-axis is its imaginary part. Take the example of an impedance of a circuit. Z is equal to 3 plus 4j. This can be represented as 3 units going to the right in the real axis and 4 units up in the y-axis. The polar representation of a sine wave can be demonstrated by two variables: its magnitude and the angle it makes with the positive x-axis. Take the earlier impedance, Z is equal to 3 plus 4j. This can be represented in a polar plane with magnitude 5 units and angle 53.1 degree. To convert rectangular to polar form, get the angle by doing the arctan of the imaginary over the real part of the earlier impedance. To get the magnitude, perform the Pythagoras theorem on the real and imaginary parts of the complex number. To convert polar to rectangular, the real part, in this case x, can be obtained by the formula r cos theta, and the imaginary part y can be obtained by the formula r sin theta. The benefit of rectangular form is that it allows you to add impedances in a series circuit, where the total impedance is the sum of all the individual impedances of the different components. This can only be done in rectangular. The benefit of the polar form is that it allows you to divide and multiply impedances together. This is useful in applying to the current divider law and voltage divider law. To add impedances, group all the real parts and add them. To multiply and divide impedances, group all the magnitude and perform the multiplication or division operation. For the angles, if two polar forms are being multiplied, then the angles are being added. If two polar forms are dividing, then the angles are being subtracted from each other.